Okay, so we're going to draw Moore's circle given a particular element's state of stress. So in this case, we have this element and it has these normal and shear stresses loading it, that is its current state of stress. And we're tasked with drawing Mohr circles and determine the following things. We're going to determine the principal stresses in this case, the maximum in-plane shear, and the angle of the principal stress and the maximum in-plane shear. Now, to do this, we're going to draw Mohr's circle, and it has the same steps every time we do it, and these are the main steps that we have to be on the lookout for. First, we're going to draw an axis that is between sigma and tau, but the tau is drawn positively downward. It doesn't point up. Notice that it points down as a positive axis. Then we're going to draw the center of the circle, which is given by my average normal stresses. And then we're going to draw the initial state. Let's go ahead and call it point A to start it with. And that is given by the average normal stress, which is the center of the circle, at a distance sigma x minus sigma y divided by 2, similar to the first term that we had for the transformation equations. And we have tau xy for the vertical axis tau. From there, we draw the radius from C to the initial state A, and then we draw a circle. And from there, we're going to identify what the principal stresses are, what the angles are, and what the maximum shear stress should be. So what I'm going to do first is I'm going to go ahead and complete the first step, which is to draw the axis system that I'm supposed to be dealing with. So I'm going to go ahead and draw a vertical axis. Notice that this one is going to have a positive tau pointing downward. Then I'm going to go ahead and draw a horizontal axis. Oops, draw that again. And that is going to be my sigma value for the stress. What I need to do next is identify what the average normal stress is. I'm going to go ahead and do that down here. And to do that, I'm going to simply say that sigma average is sigma x plus sigma y divided by 2, just the average of the two values. That means this is 30 megapascals plus minus 20 megapascals. You keep your signs following this regular sign conventions. And my sigma average is then 5 megapascals. So what I do is I simply go ahead and zoom in. I said if each of these markings is 10 megapascals, this would be, I'm going to change the color here, this would be the center C, which is at sigma average, right? Mind that this is your sigma average. Then my next step is to identify my location of point A, or the initial state. And that is given by the location of sigma average plus sigma x minus sigma y divided by 2, and the coordinate x, tau xy, I'm sorry, and that would be the location of the initial state on the Mohr circle diagram. So A becomes 5 plus 30 minus 20 divided by 2, comma, this becomes 80 megapascals from the initial state that we have here, where this is tau xy. And we close it out, and that is in megapascals, because to keep the units consistent. And thus A is equal to 30, 80 megapascal as my coordinate system. So we're very careful here when we draw these. First, the 30 is very straightforward. That would be where the x is located. But notice that tau has a positive direction downward. So whenever we do our plot, we make it positive by going to this location, and that is my point A. This is now our location of the initial state. This A represents this current state of stress whenever we're done with Mohr circle. So if this So now what we're going to do is we're going to go ahead and identify the radius. We can calculate the radius if we want to, but physically or on the graph, this is the radius that we are trying to calculate. So now this is given by just a standard trig calculation for the radius. So let's go ahead and do that since we're here. I'm going to slide this over, and we're going to say that the radius, I'm going to change the color to match it. Our radius, then it's equal to, just like any radius in any circle, the square root of the x component and the y component. The x component being x minus sigma y divided by 2 squared plus tau xy squared. So our radius then becomes the square root of, and I'm going to do all the steps here, 30 minus 20 divided by 2 square plus 80 square. Because each of these terms is megapascals, and I square it and then take the square root, it's still megapascals. So our radius is equal to 83.82 megapascals. And it may not be something that I see on the graph, but it is that physical representation of the number that we have here. The next thing that we need to do is to draw a circle. And the way we're going to draw the circle, it's simply like you imagine. We're going to pick a circle that's going to represent my radius. So if we imagine this to be about the same radius here, and I'm going to try to hit my radius in all directions. So that's 83. This becomes 1, 2, about here, about there. So let's see if I can draw a circle that matches it. So I'm going to try to. That lines up more or less well. And that is the Mohr circle case that we have identified. Now, in it, when we have Mohr circle, it's important to identify pertinent information that we're going to be working with. The first one is going to be that this point over here, the largest of the normal stresses, is my principal stress 1. And of course, the opposite then would become principal stress 2. And if we go here to the bottom with the lowest possible distance of the circle, that becomes my maximum in plane shear. Now we can calculate these as well. So if you wish to calculate that one, it'll be, as you imagine, pretty straightforward. So looking at the graph here, I'm going to change the color to match it. The first principal stress is simply sigma average plus the radius. The second principal stress would be sigma average minus the radius. And the maximum in plane shear, of course, then is simply the radius. Just watch out for your signs depending on the location that you are dealing with. Now, the next thing that we got to pay attention to is how to calculate this number. So let's go ahead and do one by one. So in my case, I'm being asked what the principal stresses are. So I'm going to go ahead and calculate it. So what are the principal stresses? We have identified them on the circle, but we can get the number. So I'm going to reduce the size of the circle here real quick so we can see what's going on. And we have that the principal stress 1 is sigma average plus the radius. So this is 5 megapascals plus 83.82 megapascals. And we have that the first principal stress is 88.8 megapascals. The second principal stress is then sigma average minus the radius. So this becomes 5 megapascals minus 83.82 megapascals. And my second principal stress then is minus 78.8 megapascals. And if we want to identify these numbers on the circle, remember this sigma then becomes 88.8 megapascals, and sigma 2, then becomes minus 78.8 megapascals. Of course, if we find the maximum in-plane shear, stress, I should say, then tau max, it's equal to my radius, and that is simply tau max being positive 83.8 megapascals. Notice that it is positive because of the location that I have here. So this is equal to 83.8 megapascals. The next thing that I have to find, according to my question here, is going to be the angle of the principal stress and the angle of the maximum shear stress. So let's take a look at what we're expecting to see here. So I'm going to go ahead and kind of look at the circle and what we're looking for here. So when we look at this graphically, we're looking at the current state of the element. So we're going to go always from the initial state to the location of my principal stress. So in this direction is where we're moving. So we're actually moving counterclockwise, and this angle then becomes 2 theta P, or the angle of the principal stress. Notice that we could measure it here graphically, but we can also calculate it like we do with regular trigonometry. So I'm going to go ahead and do that. So if we want the angle of the principal stress, we do regular trigonometry. So this becomes a bit of a triangle that we have to deal with. And this becomes the inside angle. So the tangent of 2 theta P, just based off this graph here, is equal to the opposing side, which in my case would be the original tau xy, divided by the horizontal component that we have for this graph. Remember that this element here is sigma x minus sigma y divided by 2. So in that case, what we have is sigma x minus sigma y divided by 2. We substitute our values in, and we have 80 megapascals here. We have 30 megapascals minus 20 megapascals divided by 2. And after we solve everything, we have that our angle of the principal stress is equal to 36.3 degrees. And this is important. This is counterclockwise. Now we apply a similar logic whenever you have to find the maximum in-plane. we have to find the angle of the in-plane shear. So paying close attention here, we're going to this vertical line because it's the vertical axis associated with the center, and we're going to go from the initial state to the angle at which this occurs, and this is 2 theta s for the shear. That means if we have to find, this is the angle of principal stress, and we have to find the angle of the maximum in-plane shear, we have the same thing. We still have a similar triangle to deal with. So in this case, the orientation of the angle that we're looking for changes. So this becomes simply the tangent of 2 theta s, and that would be sigma x minus sigma y divided by 2 divided by tau xy. So we just kind of reverse the directions that we're looking at, and we have 30 megapascals minus 20 megapascals divided by 2 divided by 80 megapascals. So my angle for the maximum in-plane shear is 8.68 degrees. But notice that in this case, looking at our graph here, this goes clockwise. Now, what does that mean for my element? How does my element rotate in this case then? So let's see what the state what the state of stress of the element is once I apply the rotation. So I'm going to go ahead and make this a little small. I'm going to go to a new page. I'm going to jump through my calculations here so we can see what these angles represent. And we're going to go ahead and draw it. So again, we're gonna have the initial copy the initial state. I'm gonna go ahead and compare it, the initial state to the final state for either case, either principal stresses or maximum in-plane shear. Oops. So let's copy this so we can see what the changes are. Okay, so this is my initial state. Now, for my principal, notice that nothing changes here, everything stays the same. For my principal stress case, we're going to rotate to those 36 degrees, and we're going to do it counterclockwise. So I'm going to go ahead and kind of identify what my vertical axis is so I have an idea where I'm going with this. I'm going to go ahead and draw this on the side like this. And we're going to have a rotation over axis system that's going to be, I'm going to draw in blue, that is going to be happening at 36 degrees. So this is the rotation. Theta P, or the angle of my principal stress. What does that mean for my element? Let me see if I can get it to be a square here. Okay, not quite perfect. I'd rather draw by hand. So I'm going to go ahead. Let's see if I can edit it a bit. Displeased with this. So let me just draw it the way I would want to. So this is my new rotation of the principal stress. And what that means is that I would only see my principal stresses in action here. So I'm going to have my first principal stress, and that is 88.8 megapascals. My second principal stress, which would happen at 90 degrees from it, which would be negative in this case, would be my second principal stress, sigma 2, minus 78.8 megapascals. Actually, I should say this. This is not just minus, this is, I'm going to put it in red. I don't draw the minus if I flip the arrow. So the negative is indicated by the direction of the arrow. I have added it here. For reference. What does that mean? It means that if I draw my arrow going into the element, I don't draw the sign. If I were to draw it going out towards the outside, I would, just to maintain my sign convention. So do not include it as part of your answer if you were doing this. And of course, if I'm going to do my rotation for the maximum in-plane shear, so that would be I would have a similar case. I'm going to go ahead and draw this one in purple just to kind of make it a little different, but I'm going to draw the first axis again. So just like before, I have my standard axis that I'm going to use as a reference, but I'm rotating this 8 degrees. So a very shallow angle. I'm going to go ahead and rotate it, and it's going to be only 8 degrees this way. And that angle is clockwise. and that is theta S equal to 8.68 degrees. That's going to be my axis system. So my element now is rotated at this angle. And I'm going to have the following loads in it. First, I'm going to have the maximum in-plane shear. The maximum in-plane shear that I have is positive, so it follows the positive sign convention where this is tau max equals to 83.8 megapascals. And this is worth remembering that when the maximum in-plane shear occurs, the normal loads around the element are the average normal stresses. So this becomes, it's kind of ugly, but I'm gonna fix this axis here. Okay, so this is sigma average equal to 5 megapascals, but also at 8 degrees we have the positive drawn average. So this is also the average normal stress of 5 megapascals. And now we have the three cases. We have the initial state, we have the principal stress rotation, and we have the maximum in place rotation, all derived from our Mohr circle. Remember that this becomes the location of my principal stress, this becomes the location of my maximum in plane shear. All right, and that is all there is to this.